Hi, and welcome to our video for Calculus 1 on continuity, where we will further explore some piecewise functions and things like that, and how it relates to our calculus continuity concepts. All right, so let's say this is the question that we are asked. Find the constants a and b. So let's see where a is. So a is here and here, and b, I'll do blue, is there and there. So it's in both the second and third piece of this piecewise function. So we're going to find constants a and b such that this function, which has three pieces here to this piecewise, is continuous on the entire real number line. So how I like to tackle this problem is to remember the definition of continuity. And if you remember, a basic idea for continuity was that it had three pieces to its definition. So that the left limit would equal the right limit, of course, at the same value, which equals the function's value at that same x value. So what I need to happen here is if my first function is going to end at x equals 2 and it's going to be a whole, then I need this second curve, which starts at x equals 2, to not only have the same limit or have the same whole or value, but I also need it to be equivalent there, and it is, right? Because x is equal to 2. So let's make sure these are going to be the same. Well, let's try substituting in 2 to see where this first part of my piecewise would end. So this first function here, we'll just call this function 1, will end at a whole of 2 comma something, and we need to figure out what that something is. So if I substitute 2 into function 1 here, I get 4 minus 4 over 2 minus 2. So I'm getting 0 over 0, which from our previous sections should sort of tell you something, right? So that tells me, ooh, I have algebra to do. So this is where limits are going to be used in our continuity questions. So I'm going to come down here and say limit as x approaches 2. Now this has a side because this is coming in from the left, because again, this is ending at 2 comma something. So even if you think of a number line, right, and if here's 2 and a function's going to end at 2, then you're coming in from the left. So hopefully that sort of helps. And my curve is function 1, x squared minus 4 over x minus 2. And how did we evaluate this? Well, we said since it's 0 over 0, I know I have algebra to do. So this becomes limit as x approaches 2 from the left of the function x plus 2 times the quantity x minus 2 in factored form over the factor x minus 2. So we talked about previously that being a removable factor, right? So now I can just substitute in the 2. 2 plus 2 is 4. Okay, so this is a whole at 2 comma 4. So for my second piece here of this piecewise, I'll call it piece 2, that middle function there, I need this to start at 2 comma something. Make it so you can see that. And I need these somethings to be the same. So if this is a whole at 2, 4, I need this point to also be 2 comma 4. But if I substitute in the x value of 2 into function 2 here, I get 2 squared, so 4a plus 2b plus 3. I'm running out of space again. And so because I know that these, I just really repeated that, but I know it, if the first function ends at 2, 4, and I want this to be continuous, the second function is going to have to start at 2, 4, and I know the x values already match, so I need to make these y values match. So here's the first equation that I'm dealing with. 4 as the first y value has to equal this y value, 4a plus 2b plus 3. And I'll just subtract the 3 from both sides to make this a little bit more workable here. And I'm going to keep this because anything with two variables is going to require two equations. So now I'm going to keep going and look for another equation that relates a and b so I can then solve that system. So that deals with the point surrounding x equaling 2. So now my first curve is going to end at 2, 4, and my second curve I'm forcing to start at 2, 4. So now let's look, okay, your second function is going to start at x equals 2, and it's also going to end at 3 comma something. Okay, so what is it going to end at? Well, let's put 3 in for x and see where it ends, because it starts at 2 and ends at 3. So if I put 3 in for x, that's 9a plus 3b plus 3. Okay, well, where function 2 ends should be the same place that function 3 starts. So function 3 is going to start or starts at 3 comma something, right? Because it says it starts at 3. Now, while the second curve is going to be a hole, this is going to be a point because this is where it's or equal to 3. So that will be filled in. So I don't have to worry about the function values. I just have to make sure that both of these y values are the same. So if I put 3 in for x, I get 6, 2 times 3 is 6, minus a plus b. And so what I know is that these points must be the same. Where function 2 ends has to be where function 3 starts. So I know then that 6 minus a plus b is going to have to equal 9a plus 3b plus 3. And I'm just going to write it in a little bit more usable form here, just similar to the one we already kind of kept to the side here. So I'm going to subtract the 3. I'll add the a to both sides, and I'll subtract the b. All right. So I have these two sort of cloud or bubbled equations, both with two variables. Now I'm in something that we learned prior, and I'm just trying to solve the system. So I'm going to write one on top of the other. And I like to use elimination. You certainly could use substitution or something else like that. I'm just going to multiply, for example, maybe this bottom equation by a negative, so I can add down. 1 and negative 3 is negative 2, because then if I do that, my b's add to 0. All right, I'll divide by negative 6. Be careful, because some people get this far and say that it's 3. All right, so a is 1/3. So if a is 1/3, you can go back to either one of those green equations here, right, and put your a back in to solve for b. So I'll just go up here. So 3 equals 10 times a plus 2b. 3 equals 10/3 plus 2b. So I can subtract 10/3. So 9/3 minus 10/3 gives me negative 1/3. Divide by 2. And there I have it. And it asked me for the values of a and b that are going to make this piecewise continuous. And so what I'm forcing is that where one function will end, another function will start. So if you graph piecewise functions in general, maybe one function is a parabola, maybe that's piece 1, and maybe there's a hole there. Well, in order for this to be continuous with the next piece of the piecewise, I would need to fill in this point and start from there. Okay, so let's just pretend this is piece 1 and this is piece 2 of my piecewise function. That's how you're going to make it continuous. you're continuous throughout the curve itself, then the exchange between curve 1 and curve 2 needs to be seamless. You should not have to pick up your pencil when you're drawing that curve. So we're really paying attention to those points of exchange. So even if you had 3 points of exchange, because maybe you have a line and a parabola and another line, what you want to make sure happens is if this is curve 1, curve 2, curve 3, okay, that all along the way, this exchange between functions is seamless. So not only do you have a function's value there, right, but that you also have the same point where function 1 ends is the same point where function 2 begins, okay? And then the same thing is true with the exchange between function 2 and function 3, where function 2 ends, function 3 has to begin. And then some function, 2 or 3, it doesn't matter which one, or maybe it's a function 4, will close in that point, making it not a hole. Because if you have those as holes, then you're certainly not continuous still. So hopefully that helps a little bit with that for that question. Let's see what's next. So let's do that idea again, shall we? So I did a piecewise where there were 3 pieces. Now here's a piecewise where there are 2 pieces. So I have this first piece and the second piece. And let's try to make this piecewise function continuous on the real number line. Okay, well, like we talked about before, the exchange between these 2 functions is occurring at x equals 1. I am defining the function at x equals 1 on the first curve, so that will close in my point. So that's good. So I don't have to worry about evaluating the function at 1 per se, meaning there's not a third piece that might be a separate point. The function point will be along the curve, so it'll equal the limit, so that's good. And I'm only solving for b, which is only right here in this first equation, so that doesn't seem all that bad. All right, so I'm going to sort of set this up the same way I did before, and I'm going to say function 1 ends at a point 1 comma something, and function 2 starts at 1 comma something. And again, I'm getting those ones because that's where it's telling me you are changing functions. When x is less than or equal to 1, you're on that first piece of the piecewise. And when x is greater than 1, you're on the second piece of the piecewise. Okay, so if my function ends at 1 something, we're going to put 1 into that top curve for x, right? Because 1 is your x value. So that would be b squared minus 13. And then we're going to put 1 into our second function. And the problem with that is you get 0 over 0, which means you have, in essence, a limit that you're looking at. And in this case, since we wrote the limit notation on the previous one, I'm just going to go straight to sort of evaluating this function and where will my hole be. This one will be the hole, this one will be the point, right? So evaluating where my hole will be as x approaches 1. So let's just look at algebraically, how would I simplify or rewrite this rational expression? Well, the numerator is the difference of cubes. Now, if you don't remember what the difference of cubes formula is, you should recognize that 0 over 0 told you you had some algebra to do, and we worked with that algebra within our limits, right? Our techniques of algebraically simplifying some of those limits. So we can kind of look ahead and say, I want that x minus 1 factor to be removable, right? I want that to match so they divide to 1. So I already know that 1 divides in evenly. The 0 over 0 told me that as well, right? Left 0 as a remainder. So I can divide 1 out of x cubed minus 1. So it's 1x cubed, and I'm doing synthetic division. 0x squared 0x, negative 1. Don't forget your zeros when you use synthetic division. You do have to have perfect descending order for those coefficients. All right, and I use synthetic division a lot. If you don't, maybe you have this difference of cubes formula memorized. Great, go from there. 1 times 1 is 1, add down. 1 times 1 is 1, add down. 1 times 1 is 1, add down. And so here's my leftover x squared plus 1x plus 1. So I can remove those factors. They divide to 1, and I'm left with x squared plus x plus 1. That I can evaluate when x is 1. So if I put a 1 in, I get 1 plus 1 plus 1, which is 3. So now I'm just trying to solve this equation. I need this ending point to match up with this hole, so it not only will enclose the hole, but it will also make those limits equal. So the limit from the left, right, equals the limit from the right. All right, so b squared minus 13 equals 3. Add 13, take the square root, and you do get plus or minus 4. And if you'll notice, it does say find the constants, so maybe more than one, for b. And so for now, I would include both. Okay, so both of those are going to make this function continuous. And you can certainly check it. The reason there's going to be 2 is because your equation calls for b squared x. So no matter what, your first equation is going to be 16x minus 13, and then your second equation will look the same. Okay, I hope you found this video on continuity helpful, especially making piecewise functions continuous. Thanks for watching.